this version of the talk has developed a little bit over the conversation the last few days. So there's the middle section where I'm speaking about the science of diamonds is actually going to be cut down for the sake of a bit more philosophical reflection. But there are some key scientific ideas that I want to convey, and I'll point to them. But I want to begin with the reference of immortal diamonds, which some of you may be familiar. Sadly, I was actually not familiar with. That resonates with the end of a famous poem by Gerard Manley Hopkins, that nature is a Heraclitean fire and the comfort of the resurrection. I'm not going to read the whole thing, but he begins with beautiful imagery about just daily life, things coming and going. But towards the end, the part I want to highlight, in a flash, a trumpet crash, I am all at once what Christ is, since he was what I am. And this jack, joke, poor, potsherd, patch, matchwood, immortal diamond is immortal diamond. Again, I am not that well read literarily to have recognized this myself. I found about this when I was annoying my brethren, talking about what would it be like, what would it take for there to be a large planet-sized diamond that never corrupted? What would it take to actually imagine an immortal diamond? At which point, one of the brethren pointed this out to me. And that sounds like a strange thing to imagine, and it is a strange thing to imagine. But the point I want to get, the reason that I focused on that is because this talk I will submit to you is a talk in the philosophy of nature. It touches on questions of theology and is rooted in questions of theology. It touches on questions of science and is very deeply rooted in the philosophy or in contemporary science, because I believe that is what philosophy of nature should be, properly done. But it is a question of philosophy of nature, proposing a particular question about how nature not is, but how nature could be. What might be possible for nature in a strange context. Now, since this is a context of which we do not have observational evidence, and all knowledge comes through the senses, I am not going to demonstrate anything in the philosophy of nature about the resurrection. At best, what I am proposing is rhetorical. In reality, it is almost certainly more poetical. There will be aspects of it that will appeal to certain people aesthetically and others less so. And I am going to try to argue for not the reality of some planet-sized diamond, but certain principles about how we might think about what kinds of bodies might there be after the resurrection, and how they might in some way relate to the bodies that we are so familiar with now. Why the immortal diamond, then? I have found that in the study of philosophy of nature, it is helpful at times to think about very concrete situations, because as Thomists, we tend to at times think way too abstractly about things and jump to the metaphysical, and the more grounded you can be, the better. So the outline of this talk is in 4 parts. First, a brief summary or description of what I'm calling the problem of incorruptibility. It's been in the background and explicitly mentioned at various points. I'm going to skip over the beautifully laid out theology, just sort of reference 1 or 2 moments of it, and present a few possible ways to approach this problem, including my preferred approach, drawing surprisingly on St. Thomas Aquinas. Then I'm going to ask about diamonds in particular, and how exactly do diamonds corrupt? I feel like as a theoretical particle physicist, this is somewhat out of my realm, but I am very, very versed in how to break things, because that's pretty much what particle physicists think about. The best tool we have for discovering how things work is by smashing them together and seeing how they break. So this will be a talk that is much more particle physics-y than astronomy-ish, but I hope there are some ways in which it might grope towards some questions of astronomy as well. So the second part will be mostly about diamonds as they exist now, or primarily about diamonds as they exist now, and trying to draw out some very particular questions about diamonds, but through diamonds, what it means to be a body. Thirdly, I will then imagine what might it take to make one of these bodies, in particular this diamond, and actually make it immortal. What might that be like? And then there will be some final sort of philosophical and theological reflections built upon that. I'm going to try very, very hard to keep section 2 smaller than I want to, and section 4 a little longer. But first, as a philosopher of nature, I'm a strange philosopher of nature in that I like to do demonstrations, which is not very common among philosophers of nature. So I'm going to do a brief demonstration in quantum mechanics. I'm a theoretical physicist, though, so I didn't bring my safety goggles. So here is a small sort of half-filled cup of water. Here's another small half-filled cup of water. Okay. Oh, gosh. Okay. Okay. All right. Huh. All right. Quantum mechanics works. Okay. More on that later. So the problem of incorruptibility. Again, this has been, in one sense, emphasized in the last 2 talks on the nature of the question of the resurrection. But I want to point out, which has been referenced a few points, how it's helpful at times to remember that the problems we find difficult, we presume are often difficult for our own reasons, when oftentimes they have been difficult all along. It might be different in our context, but there are resources to draw on. In this question in particular, I think, Augustine says no article of Christian faith is more repudiated than the resurrection of the flesh, which in a contemporary context might be strange. And I think that has mostly to do with the theological reflections about how the resurrection, the importance of the idea of the resurrection of the flesh, different ways in which that has been brought out. And so I want to, in one sense, re-emphasize how difficult this problem is. But also there's a way in which the particular locus around which this conversation is most important is in the resurrection of this flesh, this human body right here, that we now possess. There is the doctrine of the more general resurrection of the heavens and the earth, but the central locus that is most important is about our bodies. And it's just important to kind of remember that context. So if this problem of the resurrection of the body in general can be extended beyond simply this flesh to everything else, though, there is the question of how is it that everything that we are familiar with, including our flesh, corrupts? How can the claim of being raised incorruptible be taken seriously? Again, this was already a problem for the early church, as we have seen, but it seems, at least, and perhaps arguably is, harder today. Not only is what is familiar corruptible, but everything is corruptible. Does the idea of an incorruptible body even make any sense? So I think we have seen certain ways in which sort of 4 approaches to answering the problem of incorruptibility, which parallel questions around the resurrection of the body. One is a kind of spiritualization, either just explicit denial of the need for any materiality or body, or even I would include certain kind of leaning very, very heavily on the spirituality of our spiritual bodies in the resurrection, such that you diminish and stop asking questions about its materiality. And I think there's a way in which this is, rooted in the councils of the church, is problematic from a Catholic perspective, but is part of the current Christian conversation. There is a way in which we could say, okay, fine, there's going to be a new bodies and a new earth, but it's just different. It's just made of different stuff. And this was an option, or this was known about in the ancient world. There were that physical bodies in the resurrection will be just made of a completely different kind of incorruptible matter. There were arguments about that. Our resurrected bodies will be made of the same stuff as the heavenly bodies are now, the fifth element, or more airy spiritual matter. And generally, the fathers of the church frowned upon this. The emphasis of this flesh means something about this flesh here. And by a certain, you could argue that maybe, okay, fine, human flesh will be this flesh, but all the other bodies will be this weird, airy, or resurrect, or eviternal, or incorruptible stuff, or fifth element sorts of things. But it seems like if there's going to be continuity of something physical about this body, it should be somewhat related to the continuity, the physicality of other bodies as well. A third option is what I'm calling glorified occasionalism, which is actually occasionalism, but just by means of glory. The idea of occasionalism is that physical bodies, in general, don't do anything. While it might appear that physical bodies are doing something, it's really just God acting directly. A kind of glorified occasionalism is the idea that physical bodies in the resurrection will be the same kinds of bodies that exist now, but will be prevented from corrupting or decay by God's continual and unceasing direct activity. So that it will be the exact same stuff, it's just God is pumping it full of glory, and so it doesn't corrupt. This is, in one sense, this is, I think of this as the fallback plan, in the sense that I think this can be made consistent, and from the position of faith, we can lean into that, but I find it both aesthetically and I think philosophically unhelpful, or I would like that not to be the case. I do think there is a place for this. I mean, I think if we look at how Aquinas talks about, and I think that I find very compelling, the particular powers of beatified life, the way in which the bodies of the beatified in particular are going to act, there is a great overflow of grace in the very activity of the bodies of the blessed. And I think that's a version of this kind of glorified occasionalism. But even that one is somehow constrained by what it means to be a body. And Aquinas explicitly does not think this applies to all bodies. It doesn't apply to the elements, and it doesn't apply to those in torment either. So the position I would like to argue for, which is roughly Aquinas' position, is that physical bodies in the resurrection are the same kind of bodies that exist now, with the same kinds of natural activities. But some collection of permanent changes will prevent corruptive influences from acting, or, and this is a bit of an addition, or somehow add preservative balances so that there's a new way in which things act naturally, either by, I would prefer simply removing some stuff and saying, okay, this part of nature, while present, is just not actualized in some way. Or perhaps it might be necessary to propose that there's some new kind of actuality in a natural context. And I'll say more about that later. So Aquinas definitely thought about the constrained kind of continuity, just shut off the heavens, everything's incorruptible, done. Not so easy for us. Okay, so I'm going to approach this question of constrained or elevated continuity. I'm going to focus again on the new earth. Again, while the human body is the primary locus around the social, the importance of this flesh is emphasized. Biology is really hard. So we're going to focus on physical material things. So what I'm trying to imagine is it even possible to imagine a scientifically serious, solid body which is in practice incorruptible? And given that the answer is probably no, on a straight answer, we're not going to find something around that's practically incorruptible right now. How much of physics or chemistry do we have to change to imagine such a thing? There are three sort of clarifications or principles I'm going to lean on. One is this idea of in-practice incorruptibility. Again, we need not imagine something that could never survive, or that could survive, say, this being in the center of a star, or the destruction of a space-time, or some stray particle collider that happens to be in the resurrection. We just need to, if there is something that could destroy it, we just need to make sure it never encounters that thing, so that it, in fact, will not corrupt, not that it is necessarily in principle incorruptible. Second, to learning to love the final conflagration. Now, whether you appreciate this as an aesthetical doctrine in general, at least for this question of this philosophical exercise, it's helpful that we do not need to figure out how to make such an incorruptible solid body, just whether we can avoid breaking it. And in fact, if we had a story about how to make such a body, we kind of already have a story about how to break it. Just sort of how physics works. If you can make it, you can kind of figure out how to break it. So the idea is then just imagine this thing as having existed, created directly by God, influence of the angels. And this is, again, leading on the general notion of the final conflagration that has been talked about and noted at points. And the other just thing to remember is eternity is really, really long. If some process has a finite rate, however absurdly slow, like a billion times the age of the universe, it's going to happen an infinite number of times in eternity. And if something has the tiniest chance of happening, such that it would be utterly absurd to expect it, you have to have special pleading for this thing whose probability is, so many, 1 divided by so many zeros you can imagine it. In eternity, it's so long, it actually takes special pleading to argue it's not going to happen. So the danger of probability here. So eternity is really long, and that's going to be in the background. Okay, so diamonds and how to break them. So at this point, I am going to skip a few slides just for the sake of time. So this is a Wikipedia definition of a diamond. I'm not going to read the whole thing, but just it's a solid form of the element carbon with a particular crystal structure called diamond cubic, which is important for the features of diamond. But it's interesting because of natural things. It has the highest hardness, lowest compressibility. It's an insulator, thermal conductor. It has all these amazing features. It doesn't interact with most things chemically. So it already is pretty darn stable. So that's why we're starting there. But the real question we want to ask is, what is a good sort of scientifically serious view of a diamond? What is a diamond according to contemporary science? I just note here, right, the distinction that Eddington references. Sellers has a version of this. Eddington talked about in terms of his table, the common sense table and the scientific table. Broadly speaking, right, the common sense diamond would be some hard, transparent crystal with certain physical properties. It's shiny. It might interact with things you can touch in a certain way. Whereas the scientific diamond is some cloud of particles rushing through empty space, most of which, the vast majority of which is nothing. So which of these do I want to lean on for my scientific picture? And I would argue that from a Thomistic perspective, both are necessary to understand the diamond. We have access to it through the common sense, and yet the scientific picture is telling us something real, I would argue. Some might debate with me, but something real about the internal structure and nature of the matter underlying this diamond. And so it's important to take seriously the weird quantum mechanical things that underlie this. So that's where I'm going to start. So I'm going to start with weird quantum mechanical things and work my way up. So we're asking about diamond that's made of weird quantum mechanical things. So how might you break a quantum mechanical thing? So in some cases, you just need to wait around. So there's a sense of metastability and stability. Nature, broadly speaking, seeks out local energy minima. In a classical sense, any local minimum would be perfectly stable. It would just sit there until something else came and bumped it along. In quantum mechanics, and this is hugely important, nothing sits still. There is no spot that the electron is staying at. The minimum is always, it's never actually at the bottom of the well. It's always a little bit above it. There's always some sort of kinetic energy that, and we'll say a little bit about that later. Nothing stops. So there's always a possibility that even if you're in some local minimum, that you might jostle around enough to end up in some other minimum. So if there is both some lower minimum nearby, so you happen to be sitting in minimum 1, jostling around, and either and just get enough jostling to hop over this bump down to minimum 3, you're going to, there's a very good chance you're going to get there, provided there is, and this is way too sketchy in some ways, a physical path to access that minimum over there. It's going to vary depending on what scale you're talking about and what kind of aspects of quantum mechanics you're talking about. But the higher state, then, we call is only metastable. It might stay there for a while, but there's a very, very good chance that eventually it's going to hop over into this more stable state. Only an energy minimum with absolutely no path, quote unquote, to a lower minimum is actually stable. But if it is stable, physicists understand that as in infinite sense. It will just stay there. It's not at rest, but it will stay in the state that it's in. So as a kind of concrete example, just to kind of give us a clear sense of, hopefully a clear sense of this, these two principles, this is a picture of sort of standard nuclear decay. I don't want to go into the whole picture of things, but the big thing, the rough idea here is that along this bottom row, we're getting to decreasing mass. So as we move to the right, we're getting to lower energy states in general. It turns out also, if you're in a particular mass, generally going up gets you to a lower energy state as well. And so for nuclei, there are, generally speaking, two ways you could move from being in one energy state to another. Either the alpha decay, which is this sort of diagonal line, or the straight up line, which is the beta decay. This involves conversion of a proton to a neutron, particles going out. For now, the point I want to make is that you don't, if you're in an unstable state, you don't just go anywhere. You go in a particular place. Sometimes there's multiple options, there's multiple pathways, but you tend down certain pathways until you get to some actual minimum with respect to the physical system you're talking about. So that by the time we get way down here to where we have thallium and lead, we talk about that as being a stable isotope. There is no path by which that isotope, that particular nuclei, can jump to a lower energy minimum. And at least in principle, if you could imagine taking that stable lead nuclei and isolating it from everything else in the physical universe, in theory, it would be a lead nuclei forever. Now, again, quantum mechanics, there might be some frustration there, but we'll get to that. The second way to break quantum mechanical things is just to hit it hard enough. This might seem obvious, but if you're in a local minimum, you get enough energy to not get knocked out of the minimum, you end up somewhere else. For the sake of time, I mean, you need to hit things with the right tool, though. So not any kind of thing will interact with any other kind of thing, and you need to aim well, not just in space, but in certain contexts in terms of energy. You need to hit something with the right energy to actually make certain kinds of transitions. That's not going to be as important for what I'm going to talk about going forward. So for the sake of time, I'm going to skip over the standard model of particle physics as much as I want to. What I want to say is what I want to focus on are the pieces and parts of the diamond. So electrons, as far as we know, are perfectly stable. There is no lower mass state that can be reached while obeying fundamental conservation laws of charge, spin, etc. There are theories by which that might not be true, but as far as we can tell, electrons are perfectly stable. It is possible to hit an electron hard enough so it stops being an electron. It's not incorruptible, but if you could isolate it from the sorts of things that would hit it hard enough, in principle, it would always be an electron. So there's the details here, right? So the sorts of things you might hit it with, one would be a positron, so the antiparticle, which would interact with any kind of electron. The other would be just sort of to hit it hard enough with the right kind of thing, usually a photon or other charged particle. The idea here, the thing to realize, though, to actually break an electron, it's hard. You need the right kind of particle coming to the right energy, and it doesn't happen often in sort of normal chemical interactions. You need something like a cosmic ray or some sort of very strong nuclear decay. Okay. What I want to argue is that there's a sense in which electrons, at least in theory, have this fundamental stability, and we want to see how far up can we push that stability such that things actually are fundamentally stable in some way. Protons, as far as we can tell, are probably stable. There are theories by which the proton could decay, but as far as we can tell, the half-life is extremely constrained to 1.67 times 10 to 34 years, longer than the age of the universe. So it's most likely, it seems, that protons are stable. So that's good. Electrons and protons were good. Again, proton interactions, you got to hit it hard. For the sake of this, I'm going to, what we'll see is the easiest thing to break are going to be the bonds between carbon atoms. It doesn't take much energy to do that. So the fact that you're more likely to break that than the proton initially. Okay. What about quarks? I'm going to skip over that. They're, technically speaking, kind of stable, but you never actually find them alone. What I want to point out, so the other piece I want to point out here, neutrons are stable, neutrons are not stable. On its own, it will decay, but if you put it into a particular kind of nucleus, it will be stable. It will stay that way. So neutrons inside of a particular kind of nucleus are, as far as we can tell, stable. So jumping up in particular to carbon, there are several unstable isotopes of carbon that will radioactively decay. but 2 that won't, carbon 12 and carbon 13, carbon 12 being the most common in nature. So while bound in a nucleus, the neutrons are stable, and that nuclei as a whole is stable. Again, you can hit it hard enough and break it, but it's stable as it is. Now here is another kind of point I want to just emphasize that I hope links the scientific picture to the higher, right? Why is it that the carbon atom is actually stable? So once you have this nuclei that's positively charged, you bring certain electrons in it. Why is it that it's stable the way it is? Because if we look at the size of, in this case, it's a helium atom, because that was the image I could find easier, the relative scale of the nucleus and roughly where the electrons are, the nucleus is, as you're saying, as a point compared to the scale of the atom. The short answer here, again, for the sake of time, is it's the not completely wrong answer, is it's related to the Heisenberg uncertainty principle. That if the electron got too close in a stable way to the nucleus, then you would have much greater information about how about where it was, so your uncertainty on where it was would get very small. But in shrinking that uncertainty about how small it is, you have much less information about how fast it's going. And so it ends up breaking out of that little trap you made for it. It's a bit more complicated, but that is the rough idea that there are ways in which the stability is not in shrinking down to nothing, but in maintaining this large structure that seems mostly empty, but is this dynamic mess of electrons moving around constantly. And that seems vague and that seems airy, that seems very weird and quantum mechanical, but it's hugely important because it helps also answer some unasked questions. Namely, why can't 2 bodies be in the same place at the same time? As far as I can tell, I don't think Aristotle ever actually asks this question. He just presumes it. And most of classical physics just presumes it's too. Bodies just sort of take up space. They just fill space, and there's full space and empty space. We actually have an answer for why a single atom fills space, right? It's rooted in very quantum mechanical principles of the Heisenberg uncertainty principle. We could also ask, okay, that's great for one atom, but what if I get a bunch of atoms together? What if I get 10 to the 23 atoms, 10 to the 30 atoms? How do I know that that atom is going to stay the same size? This, you may not, this question of the stability of the size of the atom as you get more and more together is part of the answer for why it is that 1 cup of water plus another cup of water equals 2 cups of water. And also why if you hit 2 rocks together, they might make sparks, but they don't explode. There's a way in which, but importantly, the tools we just used, the fact that you have positive and electric attraction, the fact that you have the uncertainty principle is not enough to explain the stability of large-scale structures in matter. We can actually write down equations for a kind of matter that wouldn't obey that wouldn't have obeyed the law of 1 cup of water plus another cup of water equals 2 cups of water. If electrons were basically, or if electrons were bosonic, if electrons had a different spin, if electrons had a different physical property, 1 cup of water plus another cup of water would start boiling. It would be a different volume, volume wouldn't extend in the same way. So what I want to get across is basic fundamental features about what it means to be a body that we all take for granted. And if people have taken it for granted for the vast majority of history, we actually can explain why. And we can explain why because of quantum mechanics. So I think that's a hugely important principle to keep in mind so that we don't have a too simplistic notion of what it means to be a body, of simply thinking about what's familiar, but recognizing that we can explain why things act the way that we expect them to. And we have to take that into account when thinking about the nature of what the body is. Okay, so we have our carbon nucleus. It's, again, there's all sorts of really awesome things about diamonds that I spent 6 months reading about that I'm going to skip over. The important thing about the diamond is, again, it has these physical structures rooted in the quantum mechanical reality of its chemical, of its binding structure. It forms this solid crystal lattice. And again, this is deceptive picture, right? The blue dots represent roughly where the atoms would be, but the atoms are minuscule. And what is it that's holding them in place in this lattice? It's this sea of electrons moving around, entangled in such a way that you can't actually talk about any one of the electrons, but you have to actually talk about them acting as a collective unit, holding the carbon nuclei apart in a particular way. It's a deeply quantum mechanical view of what it means to be a solid object, and the particular solid object that is a diamond. Again, because of the nature of its crystal lattice, it has one of the most compact crystal structures that helps to explain its remarkable physical properties, its hardness, thermal conductivity, etc. So, okay, under what conditions could a diamond stop being a diamond if you had it? Well, you can look at the phase diagram for carbon, right? If you heat it, so here the phase diagram, on this axis is pressure, on this axis is temperature. Generally speaking, lots of temperature, you start to liquefy or vaporize things. So we want to avoid too high of a temperature. Lots of pressure makes things more solid, and for carbon, more likely to be diamond. We are like really, really close to the origin here. And so technically speaking, diamonds are metastable at room temperature. Now, as far as I can tell, no one has ever sort of measured and observed the pure metastable shift in a diamond going into graphite. It is noticeable at higher temperatures. So when you start grinding diamonds, you see it sort of flake off as graphite in various ways. But at room temperature, it seems like diamonds are maybe on the edge of stability. Again, this has to do with thermodynamic stability versus other, but it might be the case that just left alone, the diamond might actually stay that way. And there seems to be some evidence that might be the case. That said, there are lots of ways to break diamonds. Now, you might think, well, it's just like dissolve it in a really strong acid. Not going to work. It doesn't react broadly with most chemicals. But it turns out you shine sunlight on it, and it does kind of break down a little bit, very, very slowly. So UV light, which is sort of light just beyond the visible spectrum, can actually break the bonds in a carbon atom, can, under the right conditions, spawn off a carbon atom with oxygen to carbon monoxide. You can also burn diamonds, turns out. Usually you need a lot of temperature, though, and as much oxygen as you can get, roughly 700 degrees Celsius. Okay. Also, I've been talking about diamonds as these really, really hard things, and technically speaking, they are really, really hard, and their hardness is really, really high. They're also actually kind of brittle. In comparison to other things that are also very hard and hard to compress. In fact, in certain sense, because of the nature of the crystal structure, the way it dissipates the force, it ends up more likely to get sort of twisting or tension forces that can kind of shear off a layer of the diamond. So if you have a diamond and you take a hammer to it, there's a good chance you might break a flake off. So I don't recommend it. Okay, so it's hard, but not incorruptibly hard. There is a possibility of breaking it. Okay, so given that nature of diamonds and how they corrupt, how might we imagine an immortal diamond? So what are the things we need to then avoid to keep our diamond alive? Any light or UV radiation stronger than roughly 10 eV or so. So anything beyond visible light starts to become problematic. Much higher than that and even more problematic. High temperatures. Room temperature might be okay, but the colder the better. Non-sort of compressive forces. So any kind of like real strong twisting or shearing force, that's a problem. Really low pressures. Again, as you get sort of down the pressure scale, the more it's sensitive to temperature. So it'd be really nice if there were some external pressure holding a little bit our diamond together. If you put the diamond in the vacuum, it's much more likely to dissipate away because of temperature and convert into graphite. And fire. But again, here this sort of falls under the temperature thing. If we're pretty far from 700 Celsius, we're doing okay. So if our angelic builder or God directly starts with this pure carbon-12, so only carbon-12 atoms, doesn't happen naturally, we're just going to presume that. A perfect structural lattice, no imperfections. How incorruptible is this? It's pretty decent, as long as you don't hit it too hard. As long as you don't sort of forcibly hit it with a hammer, perhaps that might be enough. Okay, can we make it bigger? How big could we make such a diamond? When you start jumping to questions of, say, a planet-sized diamond, immediate things coming to mind. Is there going to, if we put so much diamond together, is the center going to start heating up and melting? Turns out, no, I don't think this is an issue. Yes, the Earth has a molten core, but as far as we can tell, based off of reading from popular science, high temperatures in the Earth's core seem to be a mixture of primordial heat from the planet formation, so like lots of stuff smashing together with lots of kinetic energy, friction from liquids as they move around, so already having a molten core makes it easier to heat, and radiation energy, atoms decay. So if our angel does his job just right and perfectly arranges this thing with no radioactive material, then there would be a very slight pressure increase, temperature increase with the pressure, but it's nowhere near, ideal gas law where it's linear with the pressure. So there's a little bit of temperature increase, but the power of the pressure increase to overcome that temperature increase is going to mean we're almost certainly going to be solid all the way down. Now the question is, as we get bigger, is the pressure even enough? Do we just end up getting into weird torques and things as we get to a planet-sized diamond? That's the point where me as the particle physicist says, like, I can't handle more than 6 electrons, so that would be a structural engineer's job. I'd like to think if you assume the diamond is a sphere or roughly a sphere, you're doing okay, but I'm not 100% sure. Now the question is, if we put this in a vacuum, right? So our new Earth needs some sort of external pressure, some atmosphere. It probably could be air, although the oxygen might be a problem. Probably not for temperature, okay. Maybe hydrogen. If we really wanted to be safe, we could sort of presume some pure helium, noble gas, just to avoid any kind of stray chemical reactivity. And its temperature, its average kinetic energy. Now, the issue here is, again, temperature is average kinetic energy, so there's the chance of a rogue gas atom hitting the side hard enough to maybe knock something free. Again, that's perhaps rare, but we're talking infinite time. So it's not 100% clear. So we're getting there, but there's still issues. But the biggest issue, which might have been for those scientifically inclined, the obvious issue is, well, now we have to wait forever and see what happens. And there's a couple of objections that might come when you think about waiting forever on this sort of thing. The first is a particularly quantum mechanical objection that I argue is probably an unnecessary worry. But this gets into a little bit away from the physics per se and more about how to think about what quantum mechanics is and interpretation of quantum mechanics. There is, as is often talked in popular science, you sometimes hear the phrase or the conversation about quantum mechanics saying that, for instance, there is a finite probability that an electron that is, in the carbon atom in my skin will appear on the other side of the galaxy. That the wave function of any particle is infinite, stretches out forever, and so there's some finite probability it could be anywhere. Now, those probabilities are so absurdly small that we say, look, in the scale of the universe, we would never expect to actually observe it, so we're fine. As I said before, infinity of time, even a small probability, you need some sort of special pleading to avoid it. So even if the probability for an electron from the surface of the Earth to suddenly appear at the center of the Earth, that would be problematic in the sense that if you could, at the same time, get all of the electrons to appear within roughly 1 centimeter, you'd create a black hole, no longer have a nice diamond. There are certain sorts of catastrophic quantum mechanical things that people can imagine, but most of them have these absurdly tiny probabilities, and so we ignore them, rightly so. Is that a problem in infinity, in the eternity of time? I would argue that given the age of the universe, I would argue that to avoid this, I think we need a particular, there are various forms of thinking about interpretation of quantum mechanics where those sorts of really tiny probabilities end up either are cut off in various ways. Like either there's some sort of link in the individual particles to the local surroundings in some sort of decoherence form, or there's sort of thermodynamic interpretation of quantum mechanics, which says that those very, very extreme probabilities are actually really zero. They're kind of, maybe, neat science fiction, but they never actually happen, properly speaking. And so that we can sort of have some actual physical argument that that those probabilities are cut off. There's further problems, right? Again, with quantum mechanics, still, our diamond is only metastable. quantum mechanics has a weird way of sneaking out of those things, even if it seems like you have good barriers up. So maybe there would be, to think through exactly how metastable is this, the kind of metastability that could, at least in a certain context, be thought of as permanently stable, would require more detailed thought about the kinematics. The bigger problem is going to be the fact that our diamond has finite temperature, which means it's constantly giving off radiation. It's constantly radiating heat away as photons. At room temperature, this is mostly in the weak infrared, so it's not the kind of photons we're worried about breaking our diamond apart, but in the tails, it could be bad. The biggest problem is that means the temperature is constantly dropping. In one sense, that's good for our diamond, but then we end up with a liquid helium atmosphere, and it seems not so great for our new Earth, our picture of the new Earth. And this might have been the obvious thing to start with in one sense, but I wanted to emphasize it through this path because there's a way in which we might say, okay, well, let's just turn off black body radiation then. What if we just imagined this thing somehow, some way in which black body radiation just doesn't happen? Well, the problem is that the best we can tell, the very electron-photon interaction that plays a fundamental role, the same interaction plays a fundamental role both in the black body radiation and in the electrostatic attraction between electrons and protons. That's the foundation for all of stability we've been talking about. The very things that make bodies be bodies means they give off radiation. Is it possible to conceive of putting like cleaving between the interaction of the electron and photon so separating somehow the interaction of electrons that leads to binding versus the interaction that lead to black body radiation? It's not obvious how. I don't know how, and I'm not going to claim that I know how. So that seems difficult and seems like a problem. There's also the problem of I've been talking about an isolated diamond in the middle of nowhere. Is there anything else out there? In one sense, it would be nice if there's something else out there, particularly something that had like a source of heat to fight off the black body radiation. Sources of heat, though, generally have finite fuel, as we've seen from stars. Putting something near a star, it's great for a couple billion years, not for eternity. More broadly, putting one other massive object out there is going to be hugely problematic for the long-term stability of that system. Yes, there's a certain sense in which two bodies is pretty easy to work out gravitationally, but the moment you have an atmosphere on this thing, it's sloshing around, there's going to be some sort of friction, there's going to be some sort of loss. The long-term stability of that, even two-body system, is questionable. Is simply isolating our star helpful or possible or even desirable? So I'm going to conclude then with some philosophical and theological reflections on this picture. Again, I'm not at all claiming that this is what I think the resurrection is like. I'm trying to imagine what is it like to have a physical, like what might it be like to have a physical body, and what is required to argue for something of continuity between the way we understand bodies now and the way we understand bodies in the resurrection. If we even conceive of trying to solve this problem of how we might fight off black body radiation and thermodynamics or broader gravitational issues, if we think about maybe changing some natural feature, somehow cleaving the black body radiation from the solidity part, or adding a term to fight off the second law of thermodynamics, are we still in the continuity situation, or have we actually just shifted into a new matter situation? We're just talking about something completely different. If a diamond is just some combination of electron, photon, quark, and gluon fields, which follow certain Lagrangian, the rules of standard model, then in principle, yes, you're just talking about a different model. It's just a different thing. On that interpretation of thinking about what physical things are, that becomes problematic. Even more kind of contemporary arguments that try to bring in certain kinds of questions about dispositions, the way in which objects have a certain activity, a natural activity to them. Even if a diamond is just identified with the various ways in which diamonds and its component parts tend to act in various situations, I would say yes, you're back in the new matter situation. Just once you change the way the thing tends to act, you're talking about a different thing. There we go. But I would argue from a Thomistic argument, Thomistic way of thinking about this, if a diamond is actualized by a substantial form, is actualized by certain proper accidents, which carry potencies for acting in a particular way in a particular situation, the patterns of which manifest in the standard model, quantum chemistry, etc., then maybe not. There's an important caveat. Again, we only have access to substantial forms through the accidental forms. We only have access to those accidental forms in the way that they interact with us. If today we came across a diamond that did not give off thermal radiation, it would be very reasonable to infer, and probably should infer, that's probably not a diamond. Something weird is going on. But in the resurrection, we will have not only our natural mode of knowledge, but that begins in the senses, but at least for the blessed, we will have some knowledge through the beatific vision. We will know the old powers that are not active, even if they don't manifest in a particular way, or the way in which some new powers complement and balance the old and make the nature reasonable. Well, the new heavens and the new earth will almost by definition be empirically and observationally very different from the blessed in particular will recognize the continuity of natures before and after, and connection between the old creation and the new, whether we're talking about the inanimate natures or even, I would argue, our physical bodies. Simultaneous, like these new things will be simultaneously strange and yet completely familiar. They will act in really weird ways, but we will recognize them for what they were and are now. For those in torment, perhaps a small aspect of their torment might simply be the unfamiliarity of the new heavens, that all the things they're familiar with start acting in very weird ways, and they don't understand the connection. There's a slight literary reference to the image that C.S. Lewis has in The Great Divorce of heaven being too real for the damned. Roughly, the damned start walking on the grass of heaven, and it hurts their feet because it's too real for them. So, in conclusion, the points I want to get across from these various parts. Well, the glorified occasionalism is always an option. I do think aesthetically, I think that Aquinas' instinct for a constrained continuity is a valuable guiding principle. From part two, what it is to be a body is inherently dynamic and mobile in contemporary science. So there is, even in the best of circumstances, this dynamism seems to lead to some aspect of corruption, some aspect of at least sort of losing of temperature, some aspect of breaking down. And so part three, we can't simply take Aquinas' answer where God just says to nature, stop, because nature stops being nature if it stops. So if we're going to have solid bodies, there's got to be some dynamism there. But perhaps some subset of motions might be changed in a certain way to support or ensure a deeper stability. If we imagine a way in which we could sort of push back against the entropy of thermodynamics, perhaps that's also a way in which we talk about the thermodynamics of mixed bodies and higher things, leading into possible Thomistically grounded ways of talking about animals and plants even, or stars. Still, the two biggest problems are perhaps what would have been obvious to begin with: light and gravity, the heavenly motions. I don't have an answer, but I have a hope that there might be connections. In part four, I would argue that the Thomistic philosophy of nature and approach to philosophy of science can help us have a hope for a real continuity, if not in individuals, at least in the kinds of things that exist, and the relationship between what we will meet in the resurrection and what we are so used to and love in this life. So thank you very much. I'll take some questions.